Since acid-base reactions are another example of double displacement reactions, you really can already predict the products and write net ionic equations for acid-base reactions. As such, this video doesn't really break a whole lot of new ground and moves relatively quickly. If predicting products is still difficult for you, it might help to turn back to section 2.2 and reevaluate those videos first. Acid-base reactions are recognized a couple of ways. First, the whole group of reactions is named after the reactants. So if you have one reactant that is an acid and a second reactant that is a base, that is just a super great clue that you're working with an acid-base reaction. Now, second, acid-base reactions have characteristic products. A molecule of water from the proton and hydroxide and a salt forms from the leftover ions. If you forget this, no bigs, because this water molecule and this salt formula unit are just the result of a double displacement process, which you already know how to do. When predicting products, it doesn't really matter if you start with a strong or a weak acid. The resulting products will be identical. If you're asked to write an acid-base reaction, the base is always going to be strong in Gen Chem 1. Know that you need to be able to recognize weak acids, but you won't predict products for them any differently than you predict products for the strong acids. Anywho, the acid is going to donate a proton in solution. So really, instead of HA, you have aqueous ions. Similar story with the base. Instead of a formula unit, you're going to have ions. Then double displacement magic happens. The products are a salt formed from the cation of the base and the anion of the acid and one molecule of water. The states of matter are important here because they mean that we can keep going. The top row of ions illustrate what was present in the reaction mixture prior to the reaction occurring. The bottom row of ions illustrates what was present in the reaction mixture after the reaction occurred. The N+ and the A- ions are present in the same number and the same form at the beginning and the end of the reaction. They did not take place in the chemical change that occurred and are acting as spectator ions. The proton and the hydroxide, in contrast, were aqueous initially and then became part of a pure liquid. We can write a net ionic equation that describes only these ions involved in the chemical change. The net ionic equation will be identical for all mixtures of a strong acid and a strong base. Only the spectator ions will change from one Arrhenius reaction mixture to the other. Regardless of stoichiometry, the chemical change for an acid-base reaction can always be boiled down to one aqueous proton coming together with one aqueous hydroxide ion to form one molecule of liquid water. Now, I was careful in the last slide to point out that the net ionic equation given was universal to strong acid, strong base mixtures because of the dissociation involved with strong species. Remember that weak acids are weak electrolytes, and weak electrolytes involve dissociation for only a very small portion of your sample. Weak electrolytes are denoted as aqueous compounds in balanced equations, though, so it's going to be important for you to keep in mind that in reality, the majority of your weak acid sample is going to be molecules, and your net ionic equation is going to have to appear a touch different so it can tell that story. I'm going to say this is a solution of the weak acid HF, or hydrofluoric acid. Remember that while we have three strong acids that have a very similar structure to their formula, HF isn't in the list of 7 strong acids and therefore has to be weak. Hydrofluoric acid dissociates only about 5% of the time, so if we had 100 molecules of the acid, only 5 would fall apart. 95 molecules is a pretty overwhelming majority, so if we weren't going to pay attention to this balanced equation that shows the dissociation and instead had to pick just between all dissociated ions or all intact molecules to best represent our sample, you really should go with all intact molecules. The net ionic equation for a weak acid will do this very same thing to tell this very story. Let's assume we're mixing the acid with a base. Even in the net ionic equation, we will not dissociate the weak acid on the reactant side of the equation, even though it does say aqueous. We're going to read this as a portion is aqueous and dissociates, but most of it won't. Because we left the counter ion on this reactant side as part of the acid, we're going to need to have the counter ion on the product side as an actual ion. Otherwise, we can't get either the charge or the atoms balanced. Each specific weak acid will have its own unique net ionic equation that follows this general formula shown here. You'll replace the HA on the reactant side with your specific acid, and you'll replace the A- with whatever is left over once your acid donates its protons. A few additional specific examples of weak acid net ionic equations are given here. I encourage you to pause the video and see how the specific examples fit into the template at the top. Since there are only 7 strong acids, it isn't feasible to memorize the net ionic equations for every weak acid known. Instead, focus on the pattern and how new things might fit into it. While you have it paused, make sure you focus on the last 2 reactions. While it was the case that all strong-strong mixtures reduced to the same exact net ionic equation with the same exact stoichiometry, that isn't the case with our weak acids. The stoichiometry has to deviate from 1 to 1 in the last 2 examples in order to balance both atoms and charge. After precipitation reactions, acid-base reactions are almost easy peasy lemon squeezy. Very similar process, but really a lot fewer options. Work to learn the strong acids and the strong bases, and how to write net ionic equations for a strong acid strong base reaction, and then, separately, for a weak acid strong base reaction. You're not going to be asked to predict products for weak base mixtures until general chemistry 2.